In this video, we're going to look at different types of forces, some of the properties that are involved in each of those forces, and how they can be used to calculate and describe that force using numbers. We're going to start off by talking about what is the most common force that we'll see in physics class, and that is weight. Anytime you have something that has mass that is in a gravitational field like the Earth's, there is going to be a force of gravity pulling it to the center of that other object. We are going to describe weight as Fg, the force of gravity, and its mass times the gravitational constant or gravitational field strength. Fg is the force of gravity that is measured in newtons because it is a force. M is the mass measured in kilograms, not grams. You must convert it into kilograms to use this equation. And then G is the gravitational field strength. We are going to use 9.8 newtons per kilogram. This varies across the surface of the Earth. It also varies if you go to different planets. So 9.8 newtons per kilogram is the gravitational field strength roughly on the surface. You will see this number in the IB Physics data booklet as 9.8 meters per second squared. We will see later on that it's also the acceleration of gravity, but we are going to use it now as newtons per kilogram. Now, again, that's Earth's surface. This equation shows up in the IB Physics data booklet. It is here in A2. It's Fg is equal to mass times gravity. Now, this is a good time to distinguish mass versus weight. You've probably heard these terms in different science classes growing up. Mass is basically the amount of matter, how much stuff is in an object. Physically, it's the atoms that are there. If I went to the moon, I would have the same number of atoms, so my mass would not change. Weight is the force due to gravity. Now, this depends on the gravitational field. It also depends on the mass. But weight is a force and mass is the amount of the matter, which means mass is going to be measured in kilograms. And since weight is a force, weight is measured in newtons. Now, we can calculate force using that equation. If you know your mass in kilograms, if you don't, you can convert it from pounds. So, say you weigh 165 pounds, that is roughly 75 kilograms. Your weight in newtons is that 75 kilograms times 9.8 or 9.81 to give you in the ballpark of 735 or 736 newtons. Again, that G value, we're typically going to use 9.8. But there are more precise values there that you could plug in as well. Okay, that is force of gravity. We'll come and see that a little bit later. Another type of force they need to know is the force of tension. Tension is basically the force of a rope or a chain. Tension always pulls, and it always pulls in the direction that that rope is going. So here, if I have 100 newtons being pulled down, there is 100 newtons probably pulling up. If I have a pulley system that changes the direction of that rope, it is always pointing in the direction that the rope is in that moment. So here, I have a force of tension pointing in the direction that is being pulled. Here in this picture of a Pixar short, the tension force is the force going at angles. We saw some examples of this in our equilibrium notes, seeing how the directionality of those ropes really impacts the direction that the force is being applied. All right, so tension has no equation to it. We will see tension showing up as basically an equalizer. It's the pull that is making something accelerate, or a tension that is holding something in equilibrium. Another equalizing force that we will see pretty often is the normal force. This one might be a little bit less familiar to you. The normal force is essentially the force of a surface. Every surface that you have, even though it looks very rigid and hard and flat and it's not changing, if you place something heavy on that surface, it's going to cause the surface to flex just a little bit. Maybe on the atomic scale, maybe something that you're not able to see. But that flexing is causing distortion that ultimately is going to spring back. There is an equalizing force that is eventually going to push back in the other direction. So if I have a force of gravity on a bowling ball on a table, that table is going to flex, creating a force as that table is working to get back to its original position. We're going to call that force Fn. That is the normal force. In this case, we know a bowling ball sitting on the table is in equilibrium. That normal force I expect is going to be the same as the force of gravity, so those forces cancel out. Now, the normal force is always going to be in the direction perpendicular to the surface that is pushing. So if I have uh, any surface, I can look to see in which direction is that surface oriented. The normal is actually a mathematical term that means perpendicular to. So if you push on a wall, the wall pushes back on you in a direction that is equal and opposite in this case, and it is perpendicular to that vertical surface. That will come way more important once we see ramps and see that direction being an angle, not horizontal or vertical. Now, to illustrate this, this will have its flaws, but if I were to change the angle of that table, you'll see that the direction of Fn changes, but Fg does not change. Fg is always in the direction of the center of the Earth. It does not depend on the angle of that surface. Now, one thing that would change that you did not see in this animation is force Fn will actually change in its magnitude as that rotation happens. So these vectors are purely showing direction, not necessarily magnitude. So let's do some calculations. There is not going to be an equation to calculate normal force. Instead, you need to look at the picture and look at the scenario. If I have a 5 kilogram block that is sitting on a table, of course, it has mass. Mass and gravity interact to give a force of gravity. So Fg is equal to 5 times 9.8, the mass times the gravitational constant. So we have Fg is equal to 49 newtons. Now, if that 5 kilograms is in equilibrium, this table must be pushing upward with a normal force that is equal to the force of gravity, 49 newtons. All right, now let's change it a little bit. Let's say we tie a string to the box and we support up just a bit, not enough to support it all. That still has a force of gravity that's 49 newtons. So 20 newtons is not enough by itself to create equilibrium. But if my normal force remained 49 newtons, I would now have 49 plus 20, which is larger than the 49 going down, which would not be equilibrium anymore. So assuming I'm not lifting it off, accelerating it upward, our normal force is essentially now just going to be force of gravity minus the tension, which is 49 minus 20 or 29. Essentially, one easy way to think of it is what would it have to be so that the 20 and this new force add up to 49? So 20 and 29 add up to the 49. Well, that was a cool animation. Next is the elastic restoring force. This is something that you've probably experienced before as well. Anytime you have an elastic, whether it's a spring or rubber band, there is a force that is caused anytime you distort it. So, say I have this mass on a string and I pull it downward, there is what we're going to call a restoring force that is trying to pull it back up to its equilibrium point. Now, if I went above the equilibrium point, say it's a spring that can undergo tension or compression, the net force is going to continually change, but it's always going to point in the direction of kind of that middle. So we call this a restoring force. It's always toward equilibrium. So if you have a rubber band and you stretch it, the equilibrium is the unstretched length of the rubber band. If you have a spring and you compress it, the equilibrium is the unstretched length of that spring. So sometimes we'll have to really focus in on the directionality. We'll say for most purposes, down is negative and up is positive. All right. So when you have a spring or rubber band, that force it actually changes based on how much you've stretched it. So let's say we are trying to plot that. Well, the force, the more you stretch it, the more force is required to keep stretching it a little bit further. Again, imagine rubber band. If you have it stretched out really far, you have to maintain a lot of force to keep it in equilibrium because that's rubber band is stretching harder back, trying to get back to its original restoring equilibrium spot. So here, we're actually going to see a force graph that looks like this, where no, not stretching at all is no distance, no force. But then the more you stretch it, the more force is required. And we'll see later on that the area under that graph is important too. All right, this can be mathematically arranged in an equation called Hooke's law. Hooke's law is the relationship to describe this elastic force. So we will describe that force as FH. It's going to be kind of annoying because H is not in the word elastic, it's in the word hook, uh, named after Robert Hooke. And Hooke's law, remember, FH is always going to, if you're in equilibrium, always going to cancel out the force that you're pulling down or in on that spring. The equation is FH is equal to minus KX. K is some constant for that spring that we're going to call the spring constant. It has units of newtons per meter. It's basically how many newtons would you need to stretch it 1 entire meter. The stiffer the spring is, the harder it is to stretch or compress, bigger the value of our spring constant, and the easier, the more flexible that spring, the smaller that value. This is a constant that is the same for a spring no matter how much it is stretched, assuming it follows this rule. Um, but different springs are going to have different values of K. So it's constant for that spring, but not constant among all springs. X is known as the extension or displacement of the spring. It's how much it is stretched. So we are not going to measure the total length of the spring or the rubber band. We are going to measure how much different is it from its resting or equilibrium position. So notice that this is always referencing that resting spring. Um, that is where we are going to reference when we're calculating F or calculating X. This equation is in A2 as well. FH is equal to minus KX. Now let's define this a little bit more, especially that minus. Notice that when I stretch the spring in the negative direction, so if I pull down, it's going to give me a negative displacement, but the restoring force is up towards equilibrium, so positive force. Likewise, if I give it a positive displacement, the restoring force is back down, negative. Hooke's law has this weird little negative here. It just means that the force is opposite the displacement. Honestly, most of the time, the the number that we need is the magnitude, not the direction. You know that the direction is towards the equilibrium, or usually the opposite of your displacement. So every positive x will result in a negative f. That's what that negative is doing. So let's do an example. A block with a mass of 2 kilograms is suspended from a spring and it produces the displacement shown. What is the spring constant? So 2 kilograms, that is going to have a weight. Fg is 2 times 9.8 or 19.6 newtons going down. If it's in equilibrium, that 19.6 newtons must be canceled out by 19.6 newtons. We saw that happening before with the normal force of a table. Here it's a spring that is doing that canceling out to give us equilibrium. So we can say that when you stretch the spring at a or -4 meters, you're going to get an FH equal to the gravity. 19.6 newtons is equal to negative K times -4. Here, those negatives end up canceling out to give us a positive value for K. Spring constant will always be positive if, when you calculate it, you did not have a negative to cancel things out. Uh, you can just make it positive in the end if you're solving for K. It's because of that directionality thing. Typically, magnitude is what we care about. So let's put it all together in one giant problem that talks about equilibrium, gravity, spring constant, tension, all of these things. So let's say we have an object in equilibrium here that's 8 kilograms. It's being supported by this vertical, or not fully vertical, 45 or 48 degrees from the vertical rope of tension, and some horizontal spring that stretched a full 3 meters in order to keep it in equilibrium. Well, let's look at all the forces. I could redraw this as a free body diagram and say, well, there's a force of gravity going down. FH, the spring, is going to the left, and then FT is at this 48 degrees. Now, that's really tricky to think about equilibrium because the FT isn't perfectly opposite anything, but it is partly vertical and partly horizontal. So let's imagine it as the y component of FT and the x component of FT. Now we can see that the verticals should cancel and the horizontals should cancel. If you never know where to start and you have the mass of something, it's a good idea to calculate gravity. Force of gravity can be helpful to unlock some other steps. So let's do that. Fg is mass times gravity. Mass is 8, gravity is 9.8, for a total Fg of 78.4. Now, if I look at my free body diagram, Fg is opposite this Fty. So the y component of this tension, this is the only thing supporting the vertical. This spring isn't doing anything. So all 78.4 must be supported by this rope, but only the y part. So we can say, all right, that's also 78.4. Now we can draw a triangle. We can say this angled tension, Well, it's 78.4 in the y direction, and then some other amount in the x direction. That x direction I know is opposite FH. It's going to be helpful. We can find FH if we know what FTX is. So it looks like that is the opposite side. FTY, something we already know is the adjacent side. Opposite and adjacent are related by the tangent. So the tangent of 48 degrees is FTX over FTY, 78.9 or 78.4. So FTX is 78.4 times the tangent of 48 degrees, which is 87.1. All right, now I know that FTX is 87.1, which means FH, the opposite direction, is also 87.1. Now I have enough information to find the spring constant K. This equation, FH, has the K constant in there, and the problem gives me that the spring is stretched 3 meters for this scenario. So 87.1, the value that we found, the horizontal has to be, is equal to negative K times, we're going to say negative 3, again, saying that we're stretching in the negative direction. If you're stressed out about that negative, just think of it as magnitude and worry about just the numbers here. So when I do that, K ends up being 29 newtons per meter. Again, I took my free body diagram and I turned it into vertical and horizontal, however I could, and looked at all the many relationships and the equations that I knew to solve for K. All right, there's a lot in this video. You should be able to calculate the weight of an object, mass times gravity, calculate or describe the difference between mass, something that's matter, and weight, which is a force. Use a diagram to identify the direction of tension and normal forces, knowing that tension is always in the direction of the rope and normal is always perpendicular to a surface. Draw that free body diagram using all of these new forces. Describe how the stretch of a spring and its elastic force is related by a spring constant, basically Hooke's law. And then use Hooke's law to calculate and figure out the direction that's built into that equation.